All right, in this section we're going to antiderivatives, where we use derivatives to find the rate of change of a quantity from an original function. But what if we know the rate of change? Can we find the original function? In other words, what if you know the derivative, but you want to find what function did you use to get the derivative? So you're working backwards. So for example, we can find distance traveled. Remember, I call the original function the position function, from its rate of change, the velocity, or the derivative. So if we have some original function here, and then we take its derivative, then we call the original function big F of x, the derivative little f. Or you're kind of used to seeing it written as this little prime. F prime means the derivative. So the antiderivative is the original. So I'm going to tell you that x squared is an antiderivative of 2x. Because if you take the derivative of x squared, you get 2x, right? Well, there are other functions that also have this derivative of 2x. How about these? So in other words, if I take the derivative of x squared, I get 2x, the derivative of a constant, 0. Same thing here happens. So we have to pay attention to that constant. And so what we do is we just say that x squared plus c is a derivative of 2x, and we call this a family of all the antiderivatives for any constant c, because it doesn't matter what that constant is, because when we take the derivative of it, it's going to be 0 anyway. An antiderivative of x is x squared over 2. Is 2? Check it. Take the derivative of this. So if I take the derivative, bring the 2 down, of course the 2's cancel, and I get x. An antiderivative of x squared is x to the third over 3. Check it. Take the derivative of x cubed over 3, and you will see you get x squared. So as you can see, when you're taking these derivatives, you're getting the original function. An antiderivative of x cubed, x to the 4. Again, we could check it. So hopefully you're seeing the pattern of what's happening here, which is just simply our definition of this rule that says whatever the power is, add 1, and then do the same thing in the denominator. And then of course all of these would be plus c when you're finding the antiderivatives. So where we move from here is we move to what's called integration, and this special symbol here is used to denote all antiderivatives as a function f. And so this is our integration and our variable of integration, and this is what we're differentiating with respect to. So in other words, when you move forward with integration, you're going to get to a point where you're going to see numbers here. If you don't see numbers here, then there's nothing to evaluate, and that's where you do the plus c. Okay, and they call those numbers limits of integration, which you'll move on into in the next section. So I can rewrite an antiderivative as an integral. In other words, we said this would be the antiderivative, the definition with the power rule. Well, this would be the same thing written with my integral symbol, which basically says find the antiderivative. So this is a very useful table, and here's the one you see that I've been showing, this power rule, but also these others in here where I have sine, and if there's a value on that k, I end up with negative cosine 1 over k. And again, think about this piece right here. If I take the derivative of cosine, that's minus sine. Well, if I stick a minus sign out front here, the negative and the negative, got my positive sign. And then by the chain rule, if I take the derivative of the inside, I get k, and that cancels that out, leaving me with this. So you could check all of these on this side, the antiderivative, by simply going back and taking the derivative of it and seeing if you get your function back. So for example, if I want to find the antiderivative of x to the fifth, I just simply add 1 to the exponent, and then of course do the same with the denominator, and I get my answer. Okay, again, you could check it to see if I take the derivative of this, do I get that back? This being my derivative, and this being my antiderivative. If I want to find the antiderivative of 1 over square roots of x, well, I'd rewrite this as x to the 1/2. I would even bring this to the top, so my exponent would become negative. And now I have something with a power. Simply use the power rule that says to add 1 to my exponent, do the same denominator. So I've added 1. Now I'm going to flip this 1, bring it to the top, and I get my answer 2x to the 1/2 power. Or the 1/2 power means square root x. Again, this is the antiderivative, and this was my derivative. Sine of x, and you're kind of thinking about these. What did I take the derivative of to get 6? Well, minus cosine of x. Sine of 2x, notice this now has that k in there from that table, and so I use this definition, and so I'm going to have minus 1 over 2 because my k is 2, and then cosine of 2x plus c. Cosine, what did I take the derivative to get cosine? The sine. If I have something extra in here, my k in this case is going to be 1/2, because you can think of that as 1/2 x. So I'm going to have 1 over 1/2, and now I simply bring that 2 to the top. E to the x, everybody is still just e to the x. As you found out when you took derivatives of e to the something, you actually use the chain rule, so we're using the chain rule. We need to undo that piece, or from your table you have this definition, and so my k is -3, so that becomes this piece, and then I leave the e alone. And again, if you take the derivative of this, it makes sense because the derivative of e to the anything is e to the anything, and then the derivative of this piece right here would be -3, which would cancel that out. And so we also have these rules where we can pull, which is nice, we can pull constants out front. And so we do the same thing here. We just bring the constant out in front of our integral sign, so it makes it easier to find now this antiderivative and then just multiply it by the constant. The negative rule, you could think of kind of like the constant as a -1. You're just pulling the negative out front. The sum and difference rule, just splitting these up, meaning it's probably easier to find the antiderivatives individually. And so the same thing is happening here, is I split these into 2 pieces and then find their antiderivative. Find the function s of t satisfying this, and also s of 0 equals 3. Alright, so the first thing that I see here is I need to find my function, my s of t. This is the derivative. I want to find my original function, which says I'm going to work backwards and find the derivative. So the antiderivative of -3, what did I take the derivative of to get -3? -3t. The antiderivative of cosine would be sine, and of course there's my constant out front. And now I'm going to use this here, which says when I plug in 0, that this should equal 3. And so what I'm doing, I'm solving for my constant. So I plug in 3, I solve for c, and I see that c equals 3. I said c a lot, huh? And so therefore my function that satisfies all of this would be my antiderivative, plus now I have a value to plug in for my constant. Alright, a hot air balloon ascending at the rate of 12 feet per second is at a height 80 feet above the ground when we kick Jose out. How long does it take Jose to smash into the ground and die a horrible death, of course? So we know the derivative of a position function's velocity. We know the derivative of velocity is acceleration. So it told us how fast it was accelerating, so we can work backwards to find the function. So if we know acceleration, we can find the antiderivative to get velocity, then the antiderivative again to get position. And Jose. Alright, so let v of t be the velocity, s of t be our position function, or height above the ground. The acceleration of gravity near the surface of the earth, we know this, 32 feet per second. So we know this is negative because of course he's falling out of the balloon. And so our initial condition was given, our velocity at time 0 was 12. To find the antiderivative, and this is our acceleration of negative 32, would be negative 32t plus c. Using this initial condition, I can solve for c to get my actual velocity function. So I also know the velocity is the derivative of the height. It was given his height at time 0. So in other words, this information is given to me for my constant. This is velocity. I want to find the antiderivative to get my original function. So how did I go from here to here? That would be negative 32t to the first power plus 1, 1 plus 1. So I get negative 32 over 2. This, of course, becomes 2, which cancels, gives you that, and then 1 plus 1 gives you that. Antiderivative of 12 would be just 12t. And now I have a function I can. So I'm given the initial condition, I plug that in, I get c, and now I get an actual height function above the ground at time t. So all I did was I started with acceleration, worked backwards, got velocity, worked backwards, and then got my original position. So how long does it take Jose to smash to the ground and die a horrible death? Well, when he smashes to the ground would be when my position function, I have a quadratic formula, I can plug in to my quadratic formula, and I can solve to get my answer, of course ignoring the negative root.